स्काईमेट वेदर पॉडकास्ट में आपका स्वागत है। मैं हूं विवेक सिंह, मैं हूं सीटीओ स्काईमेट और ये हमारी पहली मुलाकात है इस माध्यम में, बिकॉज़ मैं इसलिए आया हूं कि हम एआई के बारे में बात कर सकें। आप सबने देखा होगा कि एआई किस तरीके से हमारे डे टू डे लाइफ में एक अभिन्न हिस्सा बन चुका है और मैं आज बात करूंगा कि किस तरीके से स्काईमेट एआई को इस्तेमाल कर रहा है बेहतर मोर एक्यूरेट फोरकास्ट आप सबके लिए लाने के लिए। थोड़ा सा मैं ओवरव्यू दे देता हूँ इससे पहले कि इस पॉडकास्ट के बारे में बात करूँ कि काफ़ी सारे वेदर मॉडल्स हैं जो दुनिया भर में इस्तेमाल किए जा रहे हैं वेदर फोरकास्ट को बेहतर बनाने के लिए। शॉर्ट में बोलूँ तो एक कन्वेंशनल तरीका था न्यूमेरिकल फिजिकल इक्वेशंस का, जो जिनको एनडब्ल्यूपी मॉडल्स कहते थे, और ये जो नया एआई के एवोल्यूशन के बाद आया है वो कुछ नए वेदर मॉडल्स हैं जो कि एक्सट्रीम वेदर इवेंट्स वगैरह को बहुत अच्छे से पहले प्रेडिक्ट कर सकते हैं। हालांकि अपने देश के डेटा पे सही से ट्रेन नहीं हुए हैं, तो हमारे जैसे वेदर एजेंसीज कोशिश कर रही हैं कि बाहर की इस टेक्नोलॉजी को इंडिया में किस तरीके से हाइब्रिड मोड में लाएं और आप तक एक बेटर वेदर फोरकास्ट लेके आएँ। इस सिलसिले में हम काफ़ी लोगों से बात कर रहे हैं, जैसे गूगल में भी हमारी बातचीत चल रही है ग्राफकास्ट के लिए। इसी संदर्भ में हमने माइक्रोसॉफ्ट में का जो वेदर मॉडल है ऑरोरा, उसके लिए उनके डायरेक्टर ऑफ रिसर्च मिस्टर केंजी टकेजा से बात करी। ये पॉडकास्ट हमने इंग्लिश में रिकॉर्ड किया था लैंग्वेज कंस्ट्रेंट्स की वजह से, बट आप तक को ये बेटर तरीके से हम समझा पाएँ, इसलिए हमने इसके हिंदी सबटाइटल्स में इसको प्रस्तुत किया है। सो आई थिंक अब शुरू करते हैं पॉडकास्ट। वेलकम टू द स्काईमेट पॉडकास्ट। आई एम विवेक सिंह, CTO of Skymet. Skymet is a weather forecasting company since 2 decades. It is pioneer in weather forecasting, and recently with the advancements of AI in this field, since last couple of years we have actually been working very aggressively in bringing AI into weather forecasting. And today we have a very special guest with us, Dr. Kenji Takeda. He is the Director of Research Incubation at Microsoft Research. And I mean, his expertise, what I would say, he has done everything. So he he is expert in AI, cloud computing, aeronautics, healthcare innovation, sustainability. And basically, he advises funding agencies and research organizations on innovation and technology strategies. So he's a kind of person who brings research into the real world. So it's great to have you, Mr. Kenji. So I would call you Kenji-san if that's okay with you. so Kenji-san, I mean, we all know that how AI has actually emerged in last couple of years. It has been since last 5 years, I would say, but in last couple of years we have seen a lot of models coming from research labs to the real life world. Maybe it's GraphCast, Pangu Weather. There are a couple of more, ForecastNet and all that. And Aurora has actually emerged as a leader on top of that. I have actually recently seen the Microsoft event as well. I was very impressed by the capabilities which Aurora showcased. And in Skymet, we are actually working very extensively in bringing AI into our weather forecasting systems. I have seen that Aurora is basically very good in forecasting extreme weather events. I've seen some demos, real world scenarios, cyclones. I mean, I've seen examples of air quality, which is a big issue coming to winters in India. So basically, this podcast will be covering all these sections, sir. And Kenji-san, let's dive into this discussion. And it's really, I'm very, very happy to have you here with us. I have given a very brief introduction, but I can't cover a 360-degree view of what you have done. So I would be very happy if you can actually tell our viewers about yourself.
Thank you, Vivek. Yeah, it's an absolute honor and pleasure to be on the podcast. Thank you so much for inviting me. So I work at Microsoft Research, so we're the research arm of Microsoft Corporation. We have labs around the world, including in India. And we work on many, many different things. And we actually spun up a new lab in what we call AI for Science a few years ago. So we do believe that the application of AI in science is possibly the most important application of AI out of any. When we think about scientific discovery and how it's essentially transformed and help us evolve as a human species. And so going beyond human language, large language models, chat GPT and those things, and actually understanding the language of nature. And so that's kind of what we're doing, and that's kind of where Aurora comes from. I've actually been at Microsoft for about almost 15 years right now. Prior to that, I was actually an associate professor in aeronautics. My PhD was actually in fluid mechanics, looking at vortex flows, very applicable to geophysical flows like weather and climate. So it's nice to be returning to some of my kind of roots of research. I spent 15 years doing computational simulations on supercomputers, working in wind tunnels, and so I'm a fluids guy by training, but been on a kind of journey through tech, and it's just really amazing to see, like you say, the advances in AI, particularly in the last few years. The sort of confluence of raw kind of brain power, just trying to understand how we can design new algorithms for AI, but also an explosion in compute and the ability to train models on huge amounts of data. So I think that combination of things, and a great team in Microsoft Research kind of really is where Aurora came from. And yeah, it's just so exciting to see how much progress is being made in AI and weather and climate. I mean, I worked on numerical weather models 2 or 3 decades ago, and yeah, so they're pretty challenging in terms of how you can get an NWTP model to behave, and the progress of all of our weather agencies around the world is tremendous, in terms of the just accuracy of forecasts and trust in the forecasts. And I think AI, it's not going to replace those models, but complements them very well. And so, yeah, looking forward to the discussion today, Vivek.
Let's discuss something about the foundation and the architecture, if you want to throw some light on that. So is this a transformer-based model or diffusion-based model, or something entirely new?
Yeah, sure. So yeah, one of the sort of genesis of Aurora really, from the research team, a bunch of hugely talented people, was when you look at AI and weather, there are a few models that were coming out, and this was a really interesting space. But what the team set out to do was to create what we call a foundation model for the Earth's atmosphere. So you can build a model a bit like kind of we used to do, or traditional machine learning, where you choose a task like weather forecasting, and you just build it for that one task. Okay. So pretty much all of the work in AI for weather has been single task for weather forecasting, typically medium range weather forecasting. The team actually said, can we go beyond that? Can we build a single model for the Earth's atmosphere that can not just do weather, but it can do climate, it can do typhoons, it can do air quality? And so that's kind of what the team did. And so in order to do that, they did have to obviously think about architectures. And there are different architectures like graph-based architectures, for neural operators and things. But the team actually did go for a transformer architecture, this 3D SWIN transformer. It's actually using a kind of computer vision approach. Okay. And so considering, the globe and sort of thinking about them as kind of pixels and then a tensor. And then using kind of an encoder and decoder architecture. And what that means is that it can be trained on different types of data. So it can be trained on data at different resolutions, different types of data, whereas most of the other AI weather models are single resolution, single type of data. And so, so that kind of design choice was pretty critical, very deliberate. In order to then be able to not just do well at weather forecasting, we can talk about that in a lot more detail, but also allow it to be extended into other areas, which is kind of why we're so excited to see what people are doing with it.
So that's actually a great insight. Basically, as I told you, I am a student in this space. I mean, a 2 decade student, I would say. So I know. It basically changes everything because if I compare it, so you have actually kind of answered my next question, that how is it different from GraphCast and Pangu Weather, where basically it is trained on Era 5. The resolution and everything, because if it is a transformer encoder model, a computer vision model, it basically changes everything. It's very interesting. So I'm actually going out of syllabus to ask you. So how do you choose the images on which to train? For example, if I'm actually training it over India, so should I basically rely on the insats and the Mosdac images, or will I have to rely on the global agencies to give me? So is there a type that is basically associated with it? I'm asking you this question because what happens is when you kind of bring these AI models into the picture and try to go into the real world, basically sometimes they are bounded by a certain type of data. For example, in GraphCast, you have to rely on ECMWF Era 5 data. There are there are versions of it where you can run GFS on GraphCast, and same with Pangu Weather. But basically, for a layman, they are very much tied to a certain sort of data. So, is that foundation also there with Aurora, or it is versatile enough to basically ingest image sources that are not only just very much specific to the kind of data on which it is trained?
Sure, no, it's a great question. So I think, yeah, in terms of it's inspired by sort of vision models. So it uses a swing transformer and a unit architecture, and that encoder and decoder. But it does use gridded data. Okay, so it's trained on reanalysis data, Era 5, which everything else is trained on, but it's also trained on forecast data, IFS HRES forecast. It's trained on CMIP6 kind of climate data. So different types of data, but it's still all gridded data. Okay, so you still generally would need to use an assimilated data set like something from ECMWF. One thing we are seeing and other people are doing is looking at, okay, how can we take a global model and sort of use it at finer resolution, for instance, or even like regional, or even getting into kind of hyper local. So some new research areas. So yeah, it is gridded data. There's some nice work going on in sort of end-to-end observation to forecast as well. I think that's a great new research area as well. But yeah, Aurora is the sort of forecast task. And yeah, we're using sort of gridded data of different kinds, but different resolutions and things, different types of data. So we can use like CAMS data from Copernicus for the air quality data sets, for instance. Yeah, so it is extremely flexible in that respect.
Have you seen scenarios where it has basically performed better than numerical weather models in certain? It's just not about extreme conditions in general forecasting terms. For let's say a skill set of a 6 hour ahead or 12 hour ahead or 3 days ahead. How is it basically better from a physical model? Better, or basically it's kind of complementing NWP model, I would say, because right now I'm setting the initial conditions based on the GraphCast. So actually I'm running an NWP model, but I'm tweaking the initial conditions based on AI models. So, I mean, because you have, a different exposure to me. So just throw some light on how how it is handling the physics part of it.
Oh yeah, I mean it's interesting, with all of these AI models, you train them, and Aurora is pre-trained again, not just on weather data but on climate data as well. And so it's what happens in Aurora is it sort of transforms that into the sort of 3D latent space, so that the sort of features and understand, in some ways encodes the physics in some way. And so that's kind of what's interesting with Aurora, is because it's trained on this very diverse data set of, over 1 million hours of data. And so the team, benchmarked this, it was published in Nature in May, so it was, fully peer reviewed. and over the last sort of year or so. So they work very hard on doing very rigorous quantitative benchmarking. So for weather forecasting at sort of 0.25 degrees, but also at 0.1. So, it's over 90%, better for target variables versus IFS, which is, the gold standard for NWP. ECMWF actually posted on their blog a comparison of all the different models, and Aurora, is significantly better, not just than IFS, but even, when you start looking at other models. One of the interesting things with Aurora is, because of its architecture, it's about the only model where you can increase the resolution very easily. So pretty much all the other AI models are operating at 0.25 degree resolution. Okay. So what the Aurora team, and the reason for that is because you have a lot of training data over decades. Okay. What's interesting at 0.1 degree accuracy, which is operational forecasting resolution. Okay. The data only exists from like 2016. So what the Aurora team did was they actually fine-tuned it. So they took the base pre-trained model, they took the data from 2016, used that as a fine-tuning set, and tuned Aurora, okay, to 0.1 degree. So Aurora operates at 0.1 degrees. ECMWF actually on their dashboard of comparing all the AI models has it running at 0.1 degrees every 6 hours. And so you can directly compare every day kind of for Europe, the forecast. And so so that's what's really interesting and that then performs very, very nicely. Obviously at higher resolution, you're going to capture more physics in some sense. One of the interesting tests they did was around sort of storm intensification. And so when you look at that, it's obviously something, it's a critical topic, but the ability for weather models to capture that physics, it's really tough. So the team actually looked at a storm called Storm Kiran, which was in 2023 that hit Europe. And they looked, and it was the only AI model that could actually capture this intensification that occurred over a sort of few hours. So all the other models kind of missed it. It increased by sort of almost 10 meters per second over a day or two. And that was using the higher resolution model. So it's a good example to show the performance of Aurora. It performs well when you look at sort of global statistics, but obviously with weather, we're actually interested in what's happening locally, and things like storm evolution. The fact we can run at higher resolution at 0.1, which is a unique feature of Aurora, is testament to kind of, again, those design decisions made very early on, even for the weather forecasting task. And yeah, it performs, as well or better than other models, out to 10 days, all of that. But yeah, this higher resolution, operational level kind of resolution is another kind of unique feature, which is really, really interesting.
Yeah, that's very interesting, because actually we also want to, we are operational here, so we have a public website app. There are millions of users basically coming every day, and in last couple of months there have been very unfortunate extreme cloudburst events in India, quite few of them, and hundreds of lives were lost, unfortunately, because we have been working very extensively there. We have kind of got very much success. We have our own cloud-based physics model which we are working on, and I think we are able to get some head start of the cloudburst. But I would like to know, have you benchmarked Aurora of any such event where it is able to actually understand the cloud physics, understand when the cloudburst can happen, or give some sort of head start? Because as you said, that because it was able to understand the storm mechanism, I'm just curious to ask. It was not there in my questionnaire, but yeah.
No, I think again, these types of events that affect so many people are kind of one of the reasons why we look at AI for weather and climate, again, like I said, as a sort of critical application. So the team, what's interesting in Microsoft is, we have different teams. We actually have a team that does weather. So if you use like Microsoft Windows or Bing, you will see kind of weather. So we have a team that actually use Aurora. And they've been looking at it for different things like sort of precipitation and things like that. So again, we can do it as like a fine-tuning task. If we have data and we can experiment with that. I'm not aware of cloudburst specifics, but again, it's something that would be very interesting to look at. And again, that's where different people in the community are actually looking at Aurora for different things. And so I think a lot of it is dependent on if you have a good data set, right? If you have a good data set, then again, this ability to fine tune, I think is, really important. And so, the ability to look at these sort of events and extreme events is something that, like I say, we are seeing people look at and has, good, looks like good results. Aurora is a research project, so it was put out there as a research project, but peer reviewed. But people are now, looking at using Aurora in applications, and we rely on those experts like yourselves who deliver this every day. You really understand how these things need to be put into practice, and so that's why we're very focused on sort of partnering and working with experts, the people who do weather and climate for a living, and provide those mission critical kind of warnings and predictions to citizens and countries. And so that's really our approach with Aurora, is to kind of work with people kind of where they're at, and sort of build up really a kind of community of people pushing this forwards. That's what we're looking at. So definitely interested in those types of problems.
Kenji-san, I'll basically like to sum up what we have discussed for our viewers only. So Aurora is a transformer-based model based on ECMWF. Please correct me if I'm wrong. It's for researchers, for students, for weather enthusiasts who will be basically going through this podcast. It's a very interesting podcast. So, so Aurora is a transform-based ECMWF gridded, based on ECMWF gridded data. It could go up to 0.1 resolution, so quite better than the other 0.25 models. It has basically shown tremendous skills in predicting extreme weather, especially the storm events and the AQI, the pollution data. A very interesting part, I basically want to understand this because so Skymet is one of the premier we have the biggest weather sensor installations in India. Mm-hmm. So the numbers could range between 50 to 60,000 rain gauges or weather stations pan India. Mm-hmm. It's a huge number when you compare it with other geographies. And we are getting this data every 10 minutes. It's a huge amount of data. You basically don't need a gridded data for that. Mm-hmm. And then we have a supply of radar, METAR, inside cloud data. So what I want to understand, can Aurora really ingest the weather observation data, or it heavily relies on the statistical historical data? It's a clear distinction. Can it do data assimilation like the NWPs, where they can ingest the observation data, or Aurora will always rely on the historical data?
Sure, no, that's a great question. It's wonderful that India's investing so heavily in observations, because it's absolutely critical. So Aurora really, as a foundation model, is focused on the forecasting task. Okay, so but lots of different types of forecasting. So it takes gridded data. It does take ERA 5, but just to sort of clarify, it can take gridded data at different resolutions and different types of data. So it has to be on a grid, but doesn't have to be ERA 5 grid. So it does take grid, you have to get it into that input format,
Good,
okay?
sure,
And
sure.
that's what it takes as a sort of input file. How you get there, obviously, is, data assimilation is a huge topic in itself,
Yeah.
very complex.
Yeah.
And there are people working on AI for data assimilation to get to that gridded state. One thing I think you were looking at with Aurora is kind of fine tuning to some of that observational data. We are looking, one of the interesting scenarios is to get to even higher resolution. You go from, 11 kilometers, say to, 5 kilometer, 1 kilometer. Can you get to 100-meter resolution with Aurora is an interesting research question. Architecturally, potentially there's no constraint there. It's just, a lot of hard work and research needs to be done, and people are looking at this. So yeah, using observation data in Aurora as is something that people are looking at. Having the observations is the most important thing. So investing in observations, physical observations, is critical. So again, that's why I'd love to talk to people about that in more detail in India. Around how Aurora can be used.
That's very interesting to know, because that is where, as you already said, that is the future of AI, where we'll be basically using not only the historical but the real observation data to do the forecast. Very interesting to know. I didn't know about that, the second project was. And now coming to the most important question, because these things are very, machine extensive, so they need a huge amount of resources to run. Not only an LWB, even running a LLM. So how do you, what is the infra requirement for an organization, a bare minimum infra requirement for a research organization, for a student who is basically studying climate and atmospheric science? Because earlier, NWP always remained as a baby for research organizations and big meteorological department because of the HPCs that were required to run those, gazillions of equations and data, and then hours of churning of that data. With AI, it has, resolved, I would say. It has basically became more accessible to the people with a certain amount of GPU power. Basically, they can run a subset of that with a lot of online platforms like Colabs and Kaggle and all that. People can get a flavor of what they want to see. Earlier, it was impossible to actually get something out of the NWP model without the machine. But right now, even they can do that. But still, to bring these things to the production, where basically you are able to pay a salary out of the forecast, I would say. So, what sort of infrastructure spend you see is there or required, or Microsoft provide some partnerships, some credits? I just want to know your thoughts about it, your insights about it, because people will love to know that if they tomorrow they want to actually start some use case, they want to, for example, cyclone landfall prediction, they want to do it using Aurora. So what they will require, or Microsoft will, please.
Sure, no, that's a great question. Yeah, so it's very interesting with AI. One of the things with these kind of pre-trained models is, you have to put a lot of effort in up front to do the training. So again, we had, 1 million hours of data. It's a huge amount of data. For training, pre-training Aurora, it used 32 A100 GPUs for about 2.5 weeks. Okay, so that's a pretty solid kind of compute job to do the pre-training. That's now available. So we have the model weights actually openly available on GitHub and Hugging Face. To do inference, however, is kind of amazingly fast. If you think about how long it takes to run the reason that we get forecasts every 6 hours is because you have to kind of, run that on a supercomputer, and it takes a while on hundreds or thousands of CPUs. So with Aurora, to do like a 10-day forecast, 6-hour intervals, takes about a minute on one GPU. Okay, so rather than running on hundreds or thousands of CPUs, you literally run for 1 or 2 minutes on a single GPU. Okay, and so that really kind of unlocks a huge lot of possibilities for people like you who do AI weather forecasting, but people who want to also try it out. And so that's one thing. The other thing, we're talking a lot about fine-tuning tasks. Yeah, so we talk about fine-tuning. That we did some work on cyclone tracks, which we can talk about, wave forecasting, air pollution. Okay, so to do fine-tuning, we need to do some more training. So these tasks, some of these tasks maybe took a couple of GPUs, maybe about 5, 6, 7 days. Okay. So it's still a few days, but it's only a couple of GPUs. Okay. And then suddenly you have a new model. What's interesting with the team with some of these models is it took maybe 4 to 8 weeks to, say, create an air pollution model or to create an ocean wave model. Now, if you're trying to do that in a traditional kind of numerical system, it could take months or years to create a model to do that task. Okay, so it's really interesting. Like, inference is super fast, but even the fine tuning is very quick. And if you think about the just how long it takes to implement these things, we're looking at weeks, not months or years, in order to create new models, fine tune. And so hopefully this will really accelerate the whole field of weather and climate. And then in order to make it really easy, like I said, we're making it openly available on GitHub and Hugging Face with the model weights. We have it under an MIT license, so anybody can use it for anything pretty much. And then the other thing is we've hosted it on something we call Azure AI Foundry. So that's where we host AI models. So things, like OpenAI models or Llama models, they're hosted on Azure AI Foundry. And so we have Aurora on there. So you don't even need to have your own GPUs. You can just go in there and you can have an endpoint, and then you can start using Aurora using kind of AI Foundry. And so that's, we try and make it as easy as possible. We make it available in different ways because people want to try it in different ways. But yeah, Azure AI Foundry, AI Foundry Labs, we actually have a kind of research kind of corner of that AI Foundry site. People can go and look there and start playing. The one thing I would say with the team, as a research team, they've done a huge amount of documentation. I used to be a researcher. I used to write research code doing this type of thing. I didn't spend that much time on documentation. I just wanted to get it done, get the paper out. So actually the team have made it very easy to use. We've had this feedback actually saying Aurora actually does have a lot of documentation. And also we have a very active kind of GitHub community as well. So if anybody is trying it and they do have problems, just post it on GitHub. The reason we do that is we want to kind of do that in the open. So anybody using Aurora, if they hit a problem, they can go to issues to see if somebody else has hit the problem. When you do sort of closed support, you often can't see what problems other people are doing. So we're really excited to see what people can do with Aurora. We want to have that feedback as we continue as Microsoft to look at this. It's kind of gone beyond Microsoft research now. We have multiple teams within Microsoft and outside Microsoft using and extending Aurora.
Thanks, Kenji-san. It was such an insightful conversation, and especially for me. I mean, it's really. I'll just after this conversation, I'll just directly jump into Aurora and like to explore things. But one final. What should be your view, or what should be you want to say to our viewers and the scientists, enthusiasts who would be basically just leave your message to them?
Sure, no, thank you. And to everybody out there, like I said, the work we do is to try and kind of make the world a better place for everyone. And so that's why we put Aurora out into the open. And we would just love to see people, across India, researchers, whether companies like yourselves, whether agencies in government, to start using Aurora, talk to us. We're very interested in different partnerships and collaborations. We have a number of those kind of spinning up in very different kind of areas. We actually have a dedicated kind of email address, aiweatherclimate@microsoft.com. It kind of comes into the broader weather and climate team at Microsoft. Really, just want to have a call to action to say we want to see what people can do with Aurora in different sort of scenarios, high impact things, particularly around things like extreme weather, all of the things you spoke about, droughts, monsoons, sub-seasonal forecasting, seasonal forecasting. There's work going on climate. The scope is huge. we as Microsoft cannot do even a small fraction of that. And so, our mission is to empower every person and organization on the planet to achieve more. And with Aurora, it's a vehicle for that, hopefully, so we can help empower the global weather and climate community.
Thanks, Kenji-san. And that brings to the end of this podcast. And this is me signing off, Vivek Singh. Thank you.
Thank you so much, Vivek. Thank you, everyone, for listening.